1, xy epsilon 2, xy epsilon I. This is a general word that I have taken. And if you start from, let's say, if you call k as ki, then this is the situation. And we reach to another end, which also is a vertex of the triangle. These epsilons can be either 1 or 2. And since this is the arguments, infinity is 1 y square, so we can replace this vertex with infinity, and we get this kind of situation. That is, there exists G in the group G, such that this one is, we are taking G as a subgroup of the modular group here. So, but that is not very important here. So we get this kind of situation. And if we continue in this way, we can, on way to the main result, we can also prove that G is a subgroup of M, but not actually subgroup, it eventually becomes equal. That was one of my earlier results in which I used the coset diagrams to prove that actually there's no difference between G and M. What it basically means, as we know perhaps, that what I'm saying is that the modular group has the presentation that I've shown you earlier. That is, it is generated by two generators, x and y, and the x and y satisfy relations as x squared is equal to 1 and y3 is equal to 1. And there is no other relation in the modular group. That the proof of this fact that I've just narrated to you was given by me in 1983 by using coset diagrams, which actually result has become now part of the encyclopedic dictionary on designs and graphs, written by Professor Peter Cameron. You can see it on the internet. So, but then if we now go from the action of the modular group on the real line, real projective line, to the action of the modular group on real quadratic rationals, then in that case, our rationals are of this type, and they satisfy these relations and make sure that n is also non-square. And if we consider a small piece of the coset diagram corresponding to the orbit under consideration, we can see that there are two possible interpretations of the statement that k, ky square vertices, one is negative and two are positive. You remember this is what we agreed upon. We proved that. But now in this case, when we are considering this action, that is, the interpretation is different. Here we do not have that kind of stuff, negative or positive. Sometimes we do have real quadratic irrational numbers which are sometimes negative and sometimes positive at the same time. If you take alpha as the number, the real quadratic irrational number, then its conjugate, that is alpha bar, may be negative. So in that case, I call them ambiguous numbers, and then soon after we call them ambiguous numbers, we realize that they play a very important role in studying the action. And you see here now, if we assume that A is greater than C and C is greater than 0, then in that case this happens. This is the logic I'm giving you why we are calling them ambiguous numbers. That in that case we notice that this will be true. It's a small number of theoretic results, very easily can be achieved, which ensures that A squares will be less than n. So there's only a finite number of, this is one of the important results that I proved and which appeared in the Bulletin of Australian Mathematical Society, that there are only finite number of possibilities for alpha, for A, then this BC, that is, which is A square minus n, this one. Yes. And in that case, we prove that there are only a finite number of such ambiguous numbers. and they occur as, obviously, as vertices of the triangle here, PQR. When they are negative, when they are positive, we have two possibilities here. If you put them in table form, and you see that P can be positive, positive, Q also negative, and here it is positive, R positive, and R here negative. Similarly here, and then you can say easily that there is only a finite number of ambiguous numbers. So in the entire diagram, which is infinite diagram, the ambiguous numbers that exist in this space, they are finite in number. Not only that, but when we start moving from one vertex to the other, eventually we will come across an ambiguous number, and once we come to an ambiguous number, we get a closed path in that space or in that diagram for that space, and then all the vertices which lie on that closed path will be the ambiguous numbers. And each ambiguous number become then a solution or a root or a zero of a quadratic equation. Therefore, they get related with this stuff, binary quadratic forms. We write it as S, ax squared plus bxy plus cy squared. It is called a reduced binary quadratic form if the coefficients of A, B, C are co-prime integers. It is called indefinite binary quadratic form. If and only if this happens, we note that roots of the reduced indefinite quadratic form, binary quadratic form, are real quadratic irrational numbers, if not rational numbers. So now we get connected with the rational. Remember in the beginning I said we're going to have real line, real projective line, and then quadratic, rational quadratic numbers, and then we'll go for the space of irrational quadratic numbers. So there they get connected here. Very easily you can see that. That now there is a logic why we want to go from one step to the other. And I said in the beginning, this is the very purpose of the talk, that I want to tell you that research is done in a sequential way, and it emerges step by step from the logical interpretations of the phenomena that we are trying to study. For example, in this case, you were initially trying to look at the action of the modular group on real projective line, but then you realize that we have to go beyond that. And then you go to the quadratic form, fields. That is quadratic rational fields. Then here you see the logic for going a step ahead of a further step, and that is you need to then look at the irrational quadratic numbers, and you also realize that they are very strongly related, those quadratic equations that I was talking about just a short while ago, where I said that we get ambiguous numbers, and hence we get the closed paths, and hence we get the quadratic equations, and therefore two solutions, alpha and alpha bar. One is positive, the other is negative, vice versa. So therefore, in that case, this whole thing gets related with the reduced binary quadratic forms. And then we need to classify them also. And there we are. We then have an equivalence relation here, this one, which basically classify them into binary indefinite reduced quadratic forms. And it's classifying them, it actually is tantamount to classifying real quadratic irrationalities or irrational numbers into orbits of the coset diagram for the modular group. So there we are, that we started with the action. We see that still is working there, of course, and if you go to the higher level and see the action itself, you see that we actually, those classes that we are talking about here as classes of the indefinite reduced quadratic forms, basically they are the ones which are giving us the orbits of the action. This is the definition of the classification that we are adopting. Next, we then have to see, because of this logic, that from here then we start looking at that what type of closed paths or circuits do we get in the coset diagram for the action of the modular group on real quadratic fields. And now here, of course, we are not excluding the irrational quadratic numbers also. There was a need to look at them from this point of view also, this whole point of view. And then we, from there, from the classes that we get of the binary quadratic forms, indefinite, etc., we basically are trying to look at the orbits that we get. Therefore, once we are in that situation, we need to then know also more about the coset diagrams themselves. In order to do that, we look at the type of closed paths we get. We realize right at the outset that we cannot have in that diagram, we can never have this kind of fragment, this kind of closed path. This is a periodic closed path. We do not get them. The reason is given there. But then the proof is given there. I'm not going to get into the proof. It's a survey. I have to compromise on many things, and I have to also apologize for being a bit technical and omitting many definitions, because that if I start doing, it will take a lot of time, and I will not be able to give you overall bird's eye view of my research that I've done in 3 decades. This is an example of the sort of closed paths we get. We start from any vertex, and if you follow the path, you will see that you come back after a number of steps, like after performing this linear fractional transformation step by step, that is xy, 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 xy square, xy, so on and so forth, and you will come back to the same vertex. And this is all a cyclic application of the word G of the modular group. We go on looking at the type of circuits we get or closed paths we get. As I said, that a closed path will definitely contain with alpha its algebraic conjugate, not the group theoretic conjugate, algebraic conjugate. Now, algebraic conjugate is there, and not only that it exists in the same closed path, the beautiful thing about it is that it actually occupies a specific place or spot in the closed path. That is what I keep on saying, that these closed paths are not haphazardly constructed by the logic of the mathematics, but they are, there is a system in them, there is a symmetry in them, which we are trying to look at, which we are trying to discover in the first place. So here at least we can understand that these not only that alpha is contained in this closed path, but alpha bar, that is the algebraic conjugate of alpha, also sits there, and it sits at a particular place, and this happens with every vertex in the closed path. It happens